I'm going to walk you through how to do the video analysis for the pumpkin drop according to the handout that we got in class. So we had to go and collect this video, and then from this video, we're going to do a video analysis, and that's going to generate the graphs. I sketched the shape of the graphs that we expect to see, and then from the graphs that we generate through our video analysis, we're going to be able to obtain number of values for these. So we're actually going to generate these graphs using video analysis, which you can open as an app in your computer. We're going to import a video that you should have saved already to your files. And so I'm going to go now to find that file, and it looks like we have it right here. So we have our video. So the first thing we want to do is start to get our video in a situation where, over a little bit, where we can start to collect data on it. And so if I'm following the guidelines for this, these were actually done when we did the lawn bowling here earlier this month. And on that handout, since it was the first time we ever did video analysis, we have a lot of really detailed instructions on what to do. So we're going to be doing dragging the scroll bar so that we can get our video on the first frame where we want to start to collect data. We have to set the scale for the video. We got to set the origin, which is where we want to call the 0 meters on the tape measure. We're going to adjust then so that every time we collect a data point, it's going to advance 5 frames from that point. So we don't have to click 500 times. We would only have to click 100 times, right? Because it's going 5 times in advance. So we're going to go through all of these. We also can hit this rectangular button up here to toggle off the videos or data tables or graphs, depending on what we're focusing on at any given time. So the first thing we needed to do was to advance, which you can click. I like to use the triangle down here. We're going to look at now, if I zoom in on the release, I want to find the frame where it leaves my hand. So it looks like right about there. So let me back up a little bit here. And we can use these two buttons if we want to go frame by frame. Get just to where it comes out of my hands, like right about there. Maybe even a couple before, right there. Okay, so this is going to be our first frame that we're going to use. Next thing would be to set the scale and the origin. So with that on the handout, it says that we are going to be using the ground to the bottom of the white sign, which actually over the summer was replaced with the number 36. So we're going to actually use the 36 sign here as our scale. There's that 36 sign. I'll zoom in on that so we can set our scale. So we go to System, we have our scale here, and so I need to get the bottom of this sign to concrete, and that should be 2 meters. So I'm going to change that to 2. So we're all good there. Now I need to set the origin. So the origin, I need to zoom out here. Where do I want to call 0? So I'm going to call the ground 0. So I'm going to move this now over. Oops. Move this over. Let me get that back to vertical. There we go. And I want to move this to, so the y-axis is the axis along which the pumpkin's going to fall. So we're going to get that line up right there. And I want to make sure that up and down wise, I want that ground to be at 0. So it's going to land probably right there on the ground. And I want to be right over top of overlapping that pumpkin right there. Okay, so now we have our scale. So 0 meters is right there. And so at this point, it's on that handout. If we look back at this, we've dragged the scroll bar to get the first frame. We went to System and then Scale. Went to System, set the origin. Now we're going to go to that gear sign on the bottom and advance that right here to say, let's go 5 frames ahead every time we collect a point. Okay, great. Now we're ready to collect data. And I can zoom in so I can see it better. And I'm going to try and click right in the middle of this pumpkin. So when I click it right there, it's going to advance 5 frames. Now I don't like that dot there, so I'm going to turn the trails off for now so it doesn't have those dots show up. And it's not moving very much because it's not moving very fast. So I'm going to keep clicking, click. And I'm going to go ahead and pause the video so you don't just sit here and watch me do this. If at this point you want to pause and get caught up on it, you're welcome to do so. And so at this point, this is my last one I'm going to do, because as soon as I click this one, you can see it splats, and I don't want to collect it once it's touched the ground. So I'm done collecting data. If I zoom out and I go back to turning the trails on, you can see all the different data points I collected, and you can see the graph over here that we have. So I'm going to go up to this rectangle button, and I'm going to toggle off the video for now because I don't need to see that. I also don't need this data table. So now I'm looking at these graphs. Now this is showing both X and Y. I don't need the left and right because it really wasn't moving left and right. So I just want the Y-axis, and then I can also do the velocity time graph along the Y-axis. And these should have the shape that I expect from my handout, right? And so if I go back to now what we expected, I should see this downward facing parabola that's starting at the vertex, where I know that the instantaneous slope right here, like the steepness right at the beginning, is flat, and that's getting steeper and steeper, steeper in the negative tilt. That means that over here, it's going to start with a zero velocity, and then that velocity is going to get more and more and more negative as time goes on. But we have numbers on the graph in our video analysis, and from those numbers, we're going to obtain values for these. You can see here, for example, if I go back to my original y versus t graph, here's that parabola that we have. Probably captured a little bit too much at the beginning, but it's okay. So this should be flat at the beginning, and then it's getting steeper and steeper and steeper. Now, one thing I can do is I can go over and click the y-axis. That's going to give me delta y, right? Or like the delta x along the vertical, meaning the height. So this is starting at 13.625 meters, and I have 0 as my final point here. So that should give me my delta y. I also can get time, because I can click on the final time, about 1.6 seconds, right? But I can't get slope because this is a parabola and area doesn't give me anything. So that doesn't really help me. So although I can get delta y in time, the other graph's going to give me a lot more. So I'm going to go to that graph. And you can see here, this should be that linear graph that we saw that starts at 0. If yours doesn't start at 0, then you probably need to you probably started too many frames after I let go of it. You need to probably start it when it was right when I was letting go of it, not when it was already falling. Then it may like start here, for example, because you just simply start collecting data when it was already moving. You're welcome to go back to the video and click a few frames earlier from where you started and just collect another point or two to get that to intercept with 0. Okay. So one thing I can get from here, if I look at the x and y axes, I can get my starting velocity, which is 0. I can get my ending velocity, which is going to be negative 16.35. And I can get the time, which is about 1.58. So I'm going to write those down. So up here, I know because, whoops, I know because this is 0 and this is negative 16.4 meters per second, that means that that's going to be the ending speed, right? My initial speed is equal to 0, and so this is going to be my ending speed. So I can go ahead and write those in. It should start at 0 meters per second. My ending speed is going to be negative 16.4 meters per second, and the time was 1.58 seconds. Now we need to get delta x and a. So we use the y-axis to get v0 and v. We use the x-axis value of 1.58 to get the time. Slope is going to give me how my velocity is changing over time. And so I can get that by doing a curve fit. It should be linear, and you can see here my slope is negative 10.8. So that's going to be my acceleration. To show that on the graph, so I can show where I'm getting that value from, I can write down that the a equals negative 10.8 meters per second squared, and I can just indicate that I got that from the slope. Now, in terms of getting the delta y, we already got that. We said that from here all the way down to the ground, this actually went pretty much to the ground, right? This delta y, or delta x, was equal to, if we remember, that was equal to 13.625. The other way we could have done this is we could have sticked with this thing and we could have done the area, right? So if I highlight this and I click view integral, that's the synonym for area, you can see here that that also gives me that negative 13.6 that we have for the height. So now I can run over to my handout and see either one of those. I used this one, so I could say it's negative 13.6 meters. But we also could have done the area, right? And said that the area gives me my delta y of negative 13.6 meters. Either one was okay. Since either one's okay, I'm going to use the one that didn't cover up my slope stuff, which is this one over here. And that would mean that this should be negative 13.6 meters. Now I can label all these on my diagram, right? Like V naught is equal to 0. We know that the pumpkin is going to be moving downward with a speed of V equals negative 16.4 meters per second. We know that the downward acceleration, the downward acceleration should be, according to our graph, negative 10.8 meters per second squared. Sorry about that right there. Our delta y is going to be from the height that it started to the height that it ended up. We said that was negative 13.6 meters. And we can put the time off to the side here. Time is equal to 1.58 seconds. And so now I've diagrammed all of those variables with each variable that has a direction expressed as an arrow. In terms of the second part of this, I have it filled out already, but we would do our force diagram. The only force acting is force gravity because there is no points of contact. It's not touching anything while it's flying in the air. That unbalanced force of gravity creates a downward acceleration that both pumpkins experience, both the little one and the small one. And if we write that force gravity as the net force that's unbalanced, set it equal to ma, we can take the additional step that's a little tricky here and set it equal to force gravity, right, is equal to mg. So we can replace force gravity with mg, and that allows us to divide out the masses. Because if we divide both sides by m, then those m's divide out. Since we know g is 9.8, that means our acceleration should be 9.8. What's important, though, to realize is that that's the mathematical proof for why the little pumpkin and the big pumpkin should both experience the same acceleration. Even though the force of gravity is bigger, the mass is also going to make it harder to accelerate, right? Because you need more force to accelerate a bigger object. So that ends up being a wash and they have the same acceleration. If you go back to our video and take a look at what we saw, pumpkins did in fact fall side by side the whole way down. Observation verified. I hope this was a help. Let me know if you have any questions. Have a great one.